So hello everybody, thank you for joining me today. I'm going to turn the camera on just to put a face to this presentation. So here we're in Colorado. My name is Ronaldo Pinto, and today I'm going to be hosting today's webinar, Calculating Transient Forces for Price Stress Analysis. I'm the Technical Sales Director for AFT. You can reach me at the email ronaldopinto@aft.com. So enough with the webcam. I'm going to turn it off and start with the presentation. So, thank you for joining me today. If you have any questions during the webinar, just type your questions down at the chat room for the GoToMeeting. And at the end, we'll have a session of questions and answers, and I'll be trying to answer your questions. If we don't have enough time, I'll send you an email with the responses to your questions. This webinar will be recorded, so you'll receive a link after the presentations with where you will be able to see it. And if you want a copy of the presentation, just shoot it as an email, and we'll send you a copy of the presentation. So let's start with today's webinar. What causes Waterhammer? Waterhammer can be caused by many effects: valve closure or opening, but some people tend to think that Waterhammer is only caused if you fully close or open the valve, but also it can be caused if you partially close or open the valve. Pump speed change, that can also be trip start of pumps or startup of pumps, relief cracking, relief valve cracking opening, rapid tank pressurization, periodic pressures, and flow conditions. So what is the problem with Waterhammer? Well, Waterhammer causes transient forces imbalances in the system. This is a result of fast-moving pressure waves, which can create temporary force imbalances. Elbow pairs are especially susceptible to forces imbalance due to the change in flow direction. Waterhammer is a sufficiently complicated process such that modeling software is usually required. Hand calculations sometimes rendered not be accurate enough, so we require the use of a software, and we'll be showing you that in this presentation. Typically, the issue with primary interest, the engineer analyst, is understanding the transient pressure extremes, because this allows the selection of pipe strength and design for equipment protection and generally safety mechanism. So the application we'll be using in this presentation is AFT Impulse, which is a leading Waterhammer software. AFT Impulse has been commercially available since 1996. and has been used to model thousands of piping of the systems transient. So let's start. Once you calculate the overpressure, what should the designer do with this value? Well, that depends on the code. The answer to this question depends on the code that you're using. If you're using B31.4, pressure transportation system for liquid hydrocarbons and other liquids, B31.4 refers directly to the maximum value of the overpressure, establishing a limit of 10% above the design pressure. Now, if you're using B31.3, it's a different story because B31.3 doesn't refer directly to a maximum overpressure value. It refers to a stress. So the maximum stress produced by the loads created by the surge pressure shall not exceed 1.33 SH, where SH is the allowable stress for the operating temperature. So what is the traditional way of calculating the force imbalance? Generally, the force uses only pressures, and what it's generally done is, here we have a case of two elbows, and we're closing a valve. The flow direction is in this sense. So we're closing a valve right here, totally closing it. This generates a pressure, an overpressure in this section that travels back and sees this first elbow at the beginning, and the other elbow on the other side has a static pressure. So there's a force imbalance that generally by traditional method is calculated by the pressure times the area on this section, pressure times the area in this section, and that gives us the total force, imbalance force, that it's the one that's used to calculate the stress in this in the pipe. This works best when fully stops quickly with no inline components, and the equation used to use this is the different pressure is equal to rho times C times delta V, where C is the wave speed, and also it's also known as celerity. And in most equation is to refer as A, which is synonymous of C. Now, complexity of the real system quickly render hand calculation useless. How do pressure upstream and downstream of inline components change and add or subtract? What if the value, if the valve is only partially closed? What other forms of energy are not considered, like friction losses, momentum changes, and area changes? So let's see an example. In this case, we have the same example that we were talking about, but now we have an inline component where we have a pressure. So we have, when we close the valve partially, we have a high pressure on the valve upstream and a low pressure downstream the valve. So the force is calculated now in a much more complex equation because we consider the two forces in the elbows and the forces in the valve. Let's see an example here that we're going to talk about, and we'll use it as a model to see how we export forces for pipe stress. We have a tank here, tank A, that is transferring fluid to another tank, and we're going to partially close a valve right here. We're going to partially close it 90% in 0.5 seconds. So here we have our system modeled in AFT Impulse. We're closing the valve, and as you can see, we're not totally closing it. We're closing it 90% in 0.5 seconds. When the valve fully closes quickly, the magnitude of the resulting pressure rise can be conservatively estimated using the equation force is equal to rho times C times delta V times A. This is also called the Joukowski equation. But what happens if we close the valve 90%? Well, one could assume that assuming the pressure rise would be 90% of the equation of the magnitude. Well, it turns out this is incorrectly because the magnitude as shown in the calculation below. So here we have calculations, the values of C rho times delta V times GCC times area. So if we use the traditional equation, we would get 150,000 pounds. And AFT Impulse, considering all the inline components, pressure and the complex equation, we get 16,000 pounds, which is much slower than what Joukowsky equation calculates. So without a good ballpark pressure rise value or manual method is not reliable, how do we apply pressure to a partially closed valve? At this point, even if we understand that if we want to do a surge pressure calculations, we will need to rely on a computer-based transient hydraulic analysis software to get a reliable data. So what else? What if we include momentum and friction losses? So now the equation is much more complex because we have to consider the momentum and the pressure on this side, the momentum and the pressure on this side, and the forces created, imbalanced forces in the inline components. So the conservation of energy tells us that the total sum of the friction forces plus the pressure times the area in both bends is equal to the conservative energy of the momentum in each side of the equation. When we use a traditional way of calculating forces, we would get an imbalanced force that it's not equal to 0. And we know that in steady state, the forces should be balanced. So this is incorrect. So the pressure should start from 0. Now, if we use all the inline components to accurately calculate the forces, then we would see that at time 0, we would get 0 forces in the steady state, and then starts the unbalanced forces to travel in the system. So the traditional way, here's a table comparing the traditional way of calculating. The traditional way of calculating the forces will give us a maximum pressure of 0.3 in the 0.3. And considering all the inline components, we would get 2.9. And the minimum pressure, the traditional way would be 0.3 minus 3.3. And here it would be 0.3. This is calculating the forces in the vertical section of the model. So let's see the same calculations on the horizontal section of the model. Here's the horizontal section. So the traditional way of calculating forces will give us minus 20 in pounds, while considering all the inline components and friction and momentum, we would get 16.5 as a maximum pressure. And the minimum pressure for the traditional way of calculating forces would be 1.6 minus 1.6. And in the considering momentum and all the friction losses, it would be 1.3. So what do we conclude with this? The use of traditional forces imbalance calculation methods can be highly inaccurate because they do not consider actual load magnitudes. Direction of maximum loads can also be incorrect, as we saw in the graph. Don't know timing of the loads, and ignore some loads like the internal loads in the inline components. Okay, so now what are the three methods that are commonly used to calculate the stresses? Static equivalent, we would not be talking about this in this webinar. Spectral analysis and history analysis. So let's start with spectral analysis. First, we have to generate the DLF curves from AFT Impulse. So we go to File, Export Forces, and we go to Caesar. Our newest version, as you will see when I show you, has other programs as well. And once we do that, it asks us, what are we going to export? So here, we create the set of forces that we're going to export. Here would be the horizontal section of the model, and this would be the vertical section of the model. So we're ready to export to Caesar 2. As I said, we should include in momentum and include friction to be more accurate in the way we calculate it. So we added in the checkbox. The newest version does these, but that includes all the forces and friction momentums by default. So now we import to the curves into Caesar 2. We go to Tools, External Interfaces, and we select AFT Impulse. Caesar 2 has a connection with AFT Impulse directly. So once we select this AFT Impulse, it brings us this screen. So now we're going to import the DLF curves that we generated in AFT Impulse. Here are the two DLF curves that we generated in AFT Impulse, and we assign the nodes where it's going to be applied to. Once we do that, then it gives Caesar gives us a message saying that all the forces are in the global X, and this should be corrected in the when the dynamic analysis is performed. And we'll see how we do that. The newest version, as I'll show you later, this allows a user to include the unit vector. So now this message is not going to be sent anymore, because Caesar will consider the direction of the forces already, because it's inputted by the user. So now, what is the next step in Caesar? We open the dynamic input, and input is almost completed, generated by Caesar itself with the interface with AFT Impulse. Spectrums has been defined, force set and cases have been created. Force direction needs to be defined, as I said, in the force set and the load cases. So now we have the force set, the DLF curve that's going to be applied. It's important to put the DLF name, the node of the name that's going to be applied. So here it's going to be applied in the node 500, and here it's going to be applied in the node 300. So now we go to the force sets. The force sets have been created for you. We have two force sets. And the reason why we have two force sets is because in the spectral analysis, force sets are applied independently. And the only correction you have to make is change the direction of the forces. So now this would be the horizontal force, and this would be the vertical force in the section of the pipe. So you have to do the same for the load cases. The load cases, you have to change the directions. As I said, spectral analysis applies the spectrums independently. So it created two load cases for you. And now you have to change the direction for each one. So this one would be the one, the horizontal section, because the node 500 is in the section and Caesar 2 in the horizontal section. And then we go to the other case, and this is the vertical section. It's applied in the Y direction. Static combination stresses have been created for you. Since forces are applied independent, two cases are created. Here's the combination. So here's the dynamic load case combined with the static case. As you know, B31.3 asks you to combine this the static case with the dynamic case to calculate the resultant force. And here's the dynamic case 2, applied dynamic case 2 added to the sustained case for the two events to be analyzed. So we're almost ready. One last step that we have to perform. We have to review the control parameters. And generally, by default, Caesar 2 comes with 33 Hertz. Since it's a fast-acting load, we should increase this number to 100 to consider all the low frequency modes below 100 require low energy to be activated. So we set it as a cutoff frequency of 100 to consider the low energy modes that will be excited by a fast acting load. So once we do this, we're ready to run the spectral analysis. And if we run it, we'll get that the system failed by 22%. Before I move on to, I'm going to bring AFT Impulse and kind of follow the steps that you have to do to generate the forces. So first, you go to analysis, you go to transient control, you go to force output, and you say which ones you're going to apply, which sections you're going to create. Like this would be the horizontal section. This would be the vertical sections where you're going to calculate the forces. And as I said, the latest version, this is Impulse 8, that it's going to be released in 1 month. Now you can input the unit vectors. And Caesar, we developed with the Intergraph people from Intergraph. It will receive the coordinates, the unit vectors. So that way, the forces will, Caesar will know in what directions they're being applied. So now, once you do that, then you run the program, and you would get in the graph the forces generated. So here it would be in the horizontal. This would be in the horizontal section, the forces, and this would be in the vertical. So once you generate the forces, you're ready to export it. To export it, you come here and file. You come to export files, And as you can see, in the latest version of the software that's going to be released in Impulse 8, we have Caesar Triflex that was in the old version. Now we have Roar for the German market, and we have Autopipe. Autopipe has been added, and it's ready to receive the forces generated by Impulse. So once you do that, you select the program where you're going to export it to. And you select all the components. Like, I want to export, because I'm going to do a spectral analysis, I want to export the horizontal and the vertical spectrum to Caesar. If I try to export it, it will ask me to send it in seconds. And we're ready to export to create the file. Okay. So this would be the spectral analysis. Now let's go for time history analysis. The input required by time history analysis is almost exactly the same as spectral analysis. Both require the same force magnitude, direction, and location. Both will incorporate the same force time data. The fundamental difference is that time history analysis, the force time data is applied directly to the model, and the response is evaluated in incremental step in time. So basically, what time history analysis does is it models the force really as it's traveling down the pipe, as a difference from spectral analysis that applies it independently to each node. Spectral analysis instead converts the force time data into a maximum response curve that is matched to the natural frequency of the piping system, and sees how much each mode contributes to the total displacement. Unlike spectral analysis, time history analysis considers the timing of the events and considers the kinetic energy of the system in motion during the event. As I said, time history analysis is much more real because it models the wave traveling down the piping system as it happens, and it's not a mathematical approximation. Don't take me wrong, spectral analysis can be also a useful tool. So both of them is up to the designer to use, whether to use time history analysis or spectral analysis. Time history analysis is not automatically created for us, so in Caesar 2, so we have to manually input more of the data to perform this analysis. Time history analysis requires milliseconds, as a difference from spectral analysis that requires seconds when importing to AFT Impulse data. So when we generate the spectrums, since they're going to be applied in each one of the sections, they must be created independently. So when we go to Impulse, we select first the horizontal, and we create the spectra that's going to be applied in node 500. And then we create the vertical section. We select the vertical section that is going to be applied in the node 300. As I said, it is convenient for the analysts to name the spectrum on the node that it's going to be applied in the pipe stress program. So once we do that, we are ready to go to Caesar 2. So we open dynamic input. We add more pulses definition to dynamic input. So now here we create, we give it the same name that impulse generated the impulse. So here we have pulse node 300 and node 500. The next step is to import the data from what was created from impulse. So now we select the spectrum name 300. First, we're going to import the vertical. We read from a file that's the one that was generated, and Caesar 2 will import the data directly from impulse, and will create this graph for us. So now the next step is to go generate the node 500 application. So now it will import, read from a file, and it will import, Caesar 2 will import this graph, which is the graph force. As you can see, the magnitude, this is not an approximation. The magnitude of the force is also imported. So this is one of the things we don't have to put the magnitude, because all the magnitudes are directly imported from the file generated by impulse. So now the next step is to define the forces, location and direction. Magnitude is already defined when the data is imported. So now we don't put the magnitude, only the direction of the force. In this case, it's minus and minus. The node that it's going to be applied to, and the force sets that it belongs to. This would be force set 1, and this would be force set 2. We create a time history load case. So here we go to load case, and we set the direction of the forces. So the load case that we're going to study are 2, because they're applied independently to each node, 300 and 500. And now the next step is to create a dynamic case. Since it's a combination, we only need to create one dynamic case. That would be dynamic case 1, combined with the static case that we're going to analyze it against. So we have the dynamic case load 1 combined with the static case for the stress analysis, factor of 1. And finally, we use the control parameters. The same as spectrum, we put the cutoff frequency 100 because it's a fast acting load, and all the loads below 100 hertz need low energy to be excited, so all of them will participate. So we change it to 100 hertz, the cutoff frequency, and the time set 5 milliseconds and duration of 10 seconds. That would be right here. 5 milliseconds the time step, and duration 10 seconds, because that is the total data that is important from Caesar. And where do we get this number from? Okay, let me bring impulse. Give me 1 second. So this is Impulse 8. So we'll bring the file that we're going to use, that we've been using to this. So the 5 milliseconds to see it, this is the one transient control. Go to force transient control. So the 5 milliseconds will come from this number here. This is not necessarily what you have to use, but it's a suggestion I give. And the 10 seconds is the time of the total time simulation that we're using. As you can see, if I generate the forces in the graph result, we go to the tab of forces, we select both forces, the horizontal and the vertical, and let's model only 5 seconds to see it better. 4 seconds. As you can see, this is the horizontal wave pressure on the, and this is the vertical and the vertical section. So what we can see from here is that the wave travels and hits first the horizontal section of the pipe, and then it hits the vertical. And the reason for this is that we're closing the valve right here, so the horizontal sees the increase of pressure first, and then the vertical. And this is what history analysis tries to model, how the stresses change as the pressure wave travels, and that's what we're modeling when we do the history analysis. As a difference in when we do spectral analysis, that it models, it calculates stresses independently applied to each node. So once we update the control parameters, we're ready to run the time history analysis, and we get that it failed by 18%, while in spectral analysis it failed by 22%. So that tells us that spectral analysis is more conservative than history analysis, and the reason for that is that history analysis is more real. It models as the wave travels, while spectral analysis analyzes each spectrum independently and not as they travel, as the wave travels down the pipe. So how do we prevent this failure? Well, the first thing that we should try to do is to slow closing the valve to a minimum of 1 second instead of 0.5 seconds. If we do that, then we would get a resultant stress of 30,000, which is below to 30,900 in the pipe stress code. So that would give us allowable. Another solution would be to add an actual restraint to the horizontal to absorb the load. But the problem with that would be that the equivalent load that the actual restraint would have to handle is 13,000 pounds. And in my experience, above 5,000 pounds is load difficult to handle for supports. So 13,000 would require a special support that could be more expensive. So a better idea is to try to lower the magnitude of load if possible. So what are the conclusions? It is important to model Waterhammer events for proper system design and operation. AFT Impulse can generate transient forces that can be easily imported to CISA2 to do either spectrum or history analysis. Traditional force estimation techniques, which rely on pressure difference, can be highly inaccurate. Manual method using the Joukowsky equation can be conservative, especially for with partially closing valve events. Partial closure of the valve can also cause failure if not done properly. We saw that we partially closed 90% in 0.5 seconds. So that can create a failure, and it's more appropriate if we close it in 1 second. Spectral analysis can be conservative compared to history analysis. Okay, so now we come to the sections of question and answer. Hopefully, so you can type down here in questions. Okay, what about the third direction, the CFT? As I said, our latest software will allow the unit direction and analysis, transient control. When you export the forces, you will have the three-dimensional directions, X, Y, and Z. X, Y, and Z. So the three directions are considered in the force. If bend is considered in both pipe segments, where is the direction change in the bend and it's considered only in one pipe and one segment? Okay. When you select the analysis for the forces, you have the force output. You have several options to calculate the. If you're going to calculate like two bends, you can use difference, or different between three sections, or you can use point. So if you have intermediate bends or whatever, you can just tell the software to calculate for the intermediate sections, telling where exactly is located the bend. So you can create different spectrum for different bends in each section using the point difference and apply it to the sections. Like I would select point, and you can calculate the force in each bend independently. If you have a pipe, two bends, then you can calculate the forces and say, okay, it starts in and pipe 4. And here you say, if you have in the case of, here we have pipe 4 and pipe 5, right? Pipe forces. So here, we tell it to calculate the different forces between pipe 4 and pipe 5, and the bend in pipe 5 is located at 40 feet, which is right in the middle of the pipe 5. So here I would be telling the software to calculate the forces between this node here and in pipe 5, the different forces between in the bend located in the middle of pipe 5. You can also, if you have an intermediate bend here, you can also say, okay, I want the different forces between. You can also do it by point, but the beauty of AFT Impulse is it calculates the difference between the two elbows and considering all the intermediate forces for the inline components. Okay, for larger systems, there are many pairs of ends and port sets to be imported to Caesar 2. What is the limit of the large data input to Caesar 2? Well, this depends on the type of analysis you're going to do. If you're going to do spectrum of history, Caesar has the data limit for Caesar 2 when you export it. If you're going to do a history analysis, I haven't found any limit, but if you're going to do a spectral analysis, support to Caesar 2. Let me run it. Caesar 2 has a limit. Okay. The program will check for you if the data Caesar can receive it. As long as it is in blue, it's okay for Caesar to receive it. If not, you don't have to export all the data. You can time limit. Like here, we're exporting 10 seconds. Really, you don't need to export all the 10 seconds of the simulation. You can limit the time you're going to export to Caesar to 5 seconds. And as you can see, the size of the file that's going to be exported is reduced to half. That way, it's easier for Caesar to handle it. But as long as it's in blue, Caesar will be able to receive it. If when it's in red, you can change the time, the amount of data you can export, and adjust it to the size that Caesar 2 can receive. The stress can be reduced by increasing the distance between elbows and valves. Really not, because the pressure imbalances, as a matter of fact, if you increase the length, the distance of the elbows, the imbalance force will last longer. As a matter of fact, like very small, very short sections between elbows last less, and the stress created, modes excited are less. So really a solution is not to increase the distance between elbows. Let me see. Trying to increase the size of this. Okay, well, thank you for your time. If you have any questions, you can send me an email. And if you want examples of each one of these cases, I can send it to you. Let me see. In addition, is there a criteria to select a judge which pair of elbows have not concerns at all, so it's required to create a force set? Yes, generally the long sections of pipes where the imbalanced force lasts longer is the elbows that you select. The ones that are very short, the wave travels very fast and the imbalanced force doesn't last long. So generally the very close pair of elbows is not a concern, like the ones that have longer sections of pipes. Again, thank you very much for your time. As I said, Impulse 8 is coming now, and has a very nice improvement, and one of them is the direction of the force. So now this would be very important to calculate like a relief valve and a point, and you can put the unit vector and determine the stresses generated when the pipe relief opens, so you can comply with the Appendix A of B31.1. And I'll be presenting another webinar regarding that case. Thank you for your time, and see you in the next sections.